This is lecture 17, part 1. And it's actually the combination of lecture 17 and first half of lecture 18. And the problem with these lectures is there are lots of examples, and the algorithms are actually very simple, so there's not much theoretical stuff to go through during these pre-recorded lectures. So I will combine them into one, and then I will put the second half of lecture 18 combined with lecture 19. In any case, we will continue from the search problem, and here we're going to switch to something called local search. So I will start with an example. The example is actually a very famous example called traveling salesperson example. And you should have heard about this in other computer science courses already, but let me explain the story behind it again. So the often used example is this one here. So a traveling salesperson try to sell something in all states, and and he or she wants to start from one state and travel through all the other states once, and then go back to the original state. So I think now people sell everything online, so I don't know why anyone would do something like this, but like there was a time when people still need to do this. So they probably want to travel the least amount of distance. Well, people travel by airplane as well, so I don't know why it's related to distance. But in any case, the original problem is this person wants to travel uh, to all states only once and back to the original state. So that's the game or the problem. And what we can do is we can use our search algorithm from before. We can start from the initial state, and then the goal state is also the same as the initial state. And it's kind of hard to add the requirement that the person needs to go through all the states, but suppose we can say limit the height, and then we can try all of them, and then we can use something like A star to figure out one of the paths has the lowest cost. So along the path, each action between two states, I mean traveling between two actual states, can be measured by the total distance, which is like the edge weight there. So we can add them up and then compare which one is the smallest. It turns out this is not a good way because the state space is huge. So we need to track through all of these. So maybe we want two things. We want something that's faster, and maybe we're okay with not exactly the optimal solution. We're okay with something that's like kind of not as optimal as the single best one. So having those in mind, we're going to re-encode the problem into something else. So we'll redefine the states not as the the actual states, and also not as the place we are in. We'll define the states as just one possible solution. So it's basically one path from the diagram here. So each path is called each state. And then we're going to define successors by using some kind of similarity measure. So we will use something like a neighboring state to denote the successor state. What I mean by neighboring state is something that's similar to the state, and each state, remember, is a path. So a neighboring state, for example, would be I could switch the order between these two states. Then I'm going to travel here, and then maybe there, and then back here, and then to the next one or something like that. So basically, I do some minor changes to the solution, and then we call these things the neighboring solutions, and we call them the successors. And we start from any random solution. So we basically randomly generate a path, and then we look at the successors, and hopefully the successors are actually close because by definition they are kind of similar solutions and they will have similar costs. So we kind of use the kind of the gradient descent idea. We're going to move from one state and gradually gets better and better, and hopefully at some point it's going to converge to the optimal one. So that's basically the goal here. Let me actually show you a demo, and then you'll understand what I mean. So here, at the beginning, it's kind of a random path, and we gradually change some small subset of the path, and then at the end, you all converge to the optimal distance, which is the smallest distance. So here, again, at the end, it converges. At the beginning, it's just completely random. And again, each one of these is a state, and the successor states are similar paths, similar solutions. And if we keep getting to better and better states, and eventually, hopefully, it will converge. So that would be our idea here. And to formalize this, what we're going to have is we don't have an initial state and a goal state. We are just trying to compare different states and find the best one. So in particular here, every state will be a solution, but we want to find the best one. The way we measure which one is better is we still use the cost function as before. So one of the solution would have the lowest cost, and another main difference is we are still traveling. I mean, yes, we were still going from one state to another, going from one state to its successors, but we don't really care about the past. So we don't really care where we came from. We don't need to keep track of those. We just need to keep track of the best state so far, because we're only interested in the end result, which state is the best solution. And this is basically the same thing as I talked about. So local search is basically searching through a state space to find the optimal one. So the goal is not to find one solution, because everything is kind of a solution, but we want to find the optimal one. So that's the main difference between local search and the search we talked about in the previous two lectures. And we're going to redefine, as I said, the successor states are just the neighbors. And one main assumption that kind of defines the way how we define neighbors is they need to be similar. So we assume similar neighbors have similar cost, and we are just making small local changes until at the end it converges to the best state. Okay, some of the applications. So the most obvious application, as I mentioned already, is gradient descent. So gradient descent is actually a local search method. And so these things can be applied to any kind of optimization problem. And optimization problems are used for everything, basically, in AI. So that's very important. And it's also used to solve these kind of traveling salesmen, or in general, these kind of very strange algorithmic problems that's not really occurring in real life, but we're still interested in solving them. And then another example of this is the Boolean satisfiability problem. It's basically how to figure out the value of a bunch of variables so that it satisfy a Boolean constraint, and it's usually called the set problem. We'll talk more about some examples in the Canvas lecture. And at the end, still the scheduling problem can be formulated as a local search problem as well. So again, we will not be talking about this here. It's usually discussed more in 577 and other algorithms calls. So we will not talk about these optimization problems. We already did. And so we'll focus on some of these very strange problems as examples. And let's actually move on to the first one, the first algorithm to do local search. It's actually the most obvious one. It's called hill climbing, and it's basically like gradient descent. We just start from a random state, so a random solution, and then we always move to the best neighbor, and then we stop until we reach some kind of local minimum. So local minimum means all neighbors are worse than the current state. So basically, if you view this like we have a cost, and at every state, we can only move to two neighboring states, which are two numbers that are close. Then we move to this smaller one, and then another smaller one until we converge. So written down formally using some mathematical notations is this. So it might help you implementing the algorithm, but we'll not go through it line by line. And the biggest problem with all of these, as you have seen before many times, is we are only going to get the local minimum. We may not get the global minimum. So for example, we have some function like this, and then we just do a few steps and it's going to get stuck here. So the way we're going to deal with this, as you have seen before as well, is we're going to start from multiple random points. So here, maybe here, maybe here, and then at some point it will converge to the minimum. And we actually know the value here, the f value here, the cost function here. Then we can compare which local minimum is the best one, and then at the end we just keep the best one. And also it says here that we don't need to keep track of the past. So we don't actually need to know where, suppose I'm here, I don't care where it came from. I just need to keep doing this until it hits the local minimum. So we don't need to worry about something like the space complexity because we don't need to keep track of a lot of stuff. Okay. So that's, as I said, we just start by picking random initial states. And then hopefully at the end we can find the best among the local minimum, and the best one is the global minimum. Okay, so for gradient descent, we have those kind of stochastic gradient descent, which is not exactly always finding the best direction. We are okay with sometimes where we're finding something that might be good, but it's not always good. Here we're going to do the same thing. So the randomness may come from the fact that we are just generate random neighbors. And the first time we hit a better neighbor, we just go to that neighbor. So instead of generating all of them, for some problem, especially very high dimensional problems, there are so many neighbors, we don't want to generate all of them. What I mean by generating, it means I don't want to evaluate the cost function on all of the neighbors. So in that case, maybe I just evaluate a few, and the first time I find something better, I just immediately move to that one, and that will make each step faster. And maybe at the beginning, it will be faster converging to some area that's closer to the local minimum, just like gradient descent. And at the end, we may still want to choose the best one. So another way to do this kind of stochastic thing that's very often applied to set problem is something like this. It's actually the idea is called stochastic hill climbing. So again, it's another version of introducing randomness when doing the search. Is just with probability p, I just pick a random neighbor. So that neighbor may be worse, but I just pick a random one. And with the remaining probability, I need to go through all the possible neighbors and find the best one.